The moon, a celestial neighbour we've gazed upon for millennia, beckons us to dream. Its silvery glow has inspired countless myths, poems and scientific inquiries. For centuries, it has been a symbol of mystery and wonder, a constant companion in our night sky. It calls us to explore beyond our familiar world. The urge to venture into the unknown is deeply embedded in our DNA. From the first humans who crossed continents to the astronauts who first set foot on the lunar surface, exploration is a fundamental part of who we are. Establishing a colony on the moon is no longer science fiction. With advancements in technology and international collaboration, what once seemed like a distant dream is now within our grasp. Engineers and scientists are working tirelessly to turn these visions into reality. It is a natural progression for humanity, a species destined to explore and push the boundaries of what's possible. Our history is filled with tales of bravery and curiosity, of individuals and nations striving to reach new frontiers. The moon is our next great challenge. A lunar colony represents a strategic foothold in space. It serves as a stepping stone for deeper space exploration, a place where we can test new technologies and prepare for missions to Mars and beyond. The moon's unique environment offers unparalleled opportunities for innovation. It offers a platform for scientific research, resource extraction, and potentially a launchpad for further exploration into the cosmos. The moon's surface is a treasure trove of information, holding clues about the early solar system and the formation of our planet. The moon's proximity to Earth makes it a more accessible destination compared to Mars or beyond. Its relatively short distance allows for quicker travel times and more frequent missions, making it an ideal location for sustained human presence. It also holds vast reserves of helium-3, a potential fuel for future fusion reactors. This rare isotope could revolutionize energy production, providing a clean and virtually limitless power source for generations to come. Imagine a world where we mine resources on the moon, reducing our reliance on Earth's fragile ecosystems. Lunar mining could alleviate the environmental pressures we face on our home planet, offering a sustainable solution to resource scarcity. Imagine observatories on the far side of the moon, shielded from Earth's radio interference, peering deeper into the universe than ever before. These lunar telescopes could unlock the secrets of the cosmos, providing unprecedented insights into the nature of our universe. This is not a fantasy. The groundwork is being laid as we speak, with international space agencies and private companies investing in lunar exploration and infrastructure. The dream of a lunar colony is becoming a tangible reality. This is the future we can build, a future where humanity takes its next giant leap and establishes a permanent presence on the moon. Together we can turn this bold vision into a lasting legacy for generations to come. The success of a lunar colony hinges on choosing the perfect location. This decision is not just about finding a spot to land, it's about ensuring the long-term sustainability and safety of human life on the moon. Unlike Earth, the moon offers no breathable atmosphere, minimal protection from radiation, and extreme temperature variations. These harsh conditions make the selection of a suitable site even more critical, as it must mitigate these challenges as much as possible. Therefore, site selection is paramount. Scientists and engineers must consider a multitude of factors, including the availability of resources, the stability of the terrain, and the potential for scientific discovery. The lunar poles have emerged as prime candidates. These regions offer unique advantages that are not found elsewhere on the moon. These regions, particularly the South Pole, contain permanently shadowed craters believed to harbour water ice. This ice is a precious resource that could be used for drinking water, growing food, and even creating rocket fuel. Water is essential for human survival, can be split into oxygen for breathing and hydrogen for fuel. The ability to produce these elements on the moon would significantly reduce the need to transport them from Earth, making lunar colonization more feasible. Additionally, some areas near the poles experience near-constant sunlight, ideal for solar power generation. This consistent sunlight can provide a reliable source of energy, which is crucial for maintaining life support systems and other essential operations. The Shackleton crater, for example, receives enough sunlight to potentially power a small city. This makes it an attractive location for establishing a permanent lunar base. Before we break ground, robotic missions will map the lunar surface in high resolution, analyzing mineral composition and searching for subsurface lava tubes. These missions will provide critical data that will inform the final site selection. These natural tunnels could provide shelter from radiation and micrometeoroids, offering a safer habitat for lunar colonists. By utilizing these natural formations, we can create a more secure and sustainable living environment on the moon. The combination of water ice, sunlight and natural shelters makes the lunar poles the ideal location for humanity's next giant leap. Constructing a habitable outpost on the moon presents a logistical challenge of unprecedented scale. The harsh environment, lack of atmosphere, and extreme temperatures make it a formidable task. Engineers and scientists must work together to develop innovative solutions to these unique challenges. Transporting large quantities of material from Earth to the moon is expensive and energy-intensive. Each launch requires meticulous planning and significant resources. The cost of sending just 1 kilogram of material to the moon can be astronomical, making it crucial to optimize every mission. The initial stages will likely involve sending prefabricated modules similar to those on the International Space Station, but designed for lunar conditions. These modules will be equipped to withstand the moon's harsh environment, providing a safe and stable base for astronauts. These modules would house essential life support systems, living quarters, and research facilities. Life support systems will ensure a steady supply of oxygen, water, and food, while living quarters will provide a comfortable space for astronauts to rest and work. Research facilities will enable scientists to conduct experiments and gather valuable data. However, relying solely on Earth-based resources is unsustainable in the long run. The cost and complexity of transporting materials from Earth to the moon make it imperative to find alternative solutions. This is where the concept of in situ resource utilization comes into play. In situ resource utilization, or ISRU, is key. This involves using materials found on the moon to support the construction and maintenance of the lunar base. By harnessing local resources, we can reduce our dependence on Earth and create a more sustainable presence on the moon. Lunar regolith, the loose dust covering the surface, can be processed into building materials. This dust, which is abundant on the moon, can be transformed into bricks, concrete, and other construction materials. This not only reduces the need to transport materials from Earth, but also provides a practical use for the moon's natural resources. 3D printing technology will play a crucial role, using lunar regolith as ink to construct landing pads, habitats, and even roads. This innovative technology allows for the creation of complex structures with precision and efficiency. By utilizing 3D printing, we can build the necessary infrastructure for a lunar base more quickly and cost-effectively. This reduces the need to transport materials from Earth, making the colony more self-sufficient. A self-sufficient moon base can support long-term human presence, enabling further exploration and scientific research. By leveraging local resources and advanced technologies, we can pave the way for a sustainable future on the moon. Section 4. Constructing our lunar outpost. A Herculean task. Building on the moon will be unlike anything we've attempted before. The absence of atmosphere means temperature fluctuations are extreme, ranging from scorching heat in direct sunlight to bone-chilling cold in the shade. Astronauts clad in advanced spacesuits with enhanced mobility and life support systems will face the daunting task of assembling the colony. Robotic assistance will be crucial, with rovers and construction bots handling heavy lifting and hazardous tasks. The colony will likely be built in phases. The initial outpost will focus on survival, with subsequent phases expanding living quarters, research facilities, and resource extraction operations. As the colony grows, it will require robust power, communication, and waste management systems, all designed to function reliably in the harsh lunar environment. Section 5. The invisible threats: radiation and the lunar environment. Life on the moon presents unique challenges. Unlike Earth, with its protective magnetic field and atmosphere, The Moon offers little shielding from cosmic radiation and solar flares. Prolonged exposure to radiation increases the risk of cancer and other health problems. Habitats will need to be radiation-hardened, possibly using thick layers of lunar regolith or incorporating water shielding. Micrometeoroids, tiny particles traveling at high speeds, pose another constant threat. While the risk of a large impact is low, even small impacts can damage equipment and puncture habitats. Reinforced structures and early warning systems will be essential for safety. Section 6. Breathing easy. Creating a sustainable atmosphere. Creating a breathable atmosphere is paramount for long-term human presence on the Moon. Plants, through photosynthesis, offer a natural solution for generating oxygen. Large-scale greenhouses will be essential, not only for oxygen production but also for cultivating food. These bioregenerative life support systems will mimic Earth's natural cycles, recycling waste products and generating fresh air and water. Additionally, water ice found in permanently shadowed craters can be extracted and purified for drinking, hygiene and oxygen generation through electrolysis. Developing efficient and reliable life support systems will be crucial for a self-sustaining lunar colony.